Hey, Science Nines, it's Manchak here, recording your first lesson of Unit D. So at this point, you should have finished off Unit C, Environmental Chemistry, and should be ready to move on to Unit D. And Unit D is a brand new unit for us where we're going to have a look at electrical principles. So I'm going to bring this up and show you what's up with it. This is from your concept checklist, which remember is located at the top of your classwork page under general information in your Google Classroom. And what we have here are four major outcomes or general outcomes for the unit that I'm going to get through over the course of the unit. Basically, this unit is about electricity and technologies that use electricity. And really, this is our first big deep dive into electricity that you've done so far in any big way, and might be the last one you do until you get on to physics in high school, if you take physics or science 30 or something along those lines. So we are going to investigate and interpret the use of devices to convert various forms of energy to electrical energy and electrical energy to other forms of energy. So we'll talk a little bit about energy conversion, which is a big idea in science in this unit, and we'll look at going from one form of energy to electricity and from electricity to another form of energy. So we'll play around with those. We're going to describe technologies that transfer and control electrical energy. So we're going to look at things that use electrical energy and what they do and what they're used for. We'll identify and estimate energy inputs and outputs, for example, devices and systems, and evaluate the efficiency of these energy conversions. One of the big ideas in science also is this idea of efficiency, and efficiency leads to us having more money needed or less money needed to operate something to do. It's an efficiency thing, and it's a super big important idea in sustainability, changing the environment, those kinds of things. So I will talk a lot about efficiency in this unit and in other classes later on as well. And then the last general outcome is we're going to describe and discuss the societal and environmental impacts of the use of electrical energy. So we'll have a look at how it impacts us as a society and what we can do about the environmental implications. And in particular, I think that word efficiency is going to come up a fair bit when we get into that. There are 5 concepts in the unit, and D1 through D5, and we're going to go and start to tackle D1 today, and then for each subsequent week we'll tackle another concept. Yeah, so that's basically our plan, and we're moving into Unit D. I'm excited to do this one. It's a very practical unit. I think you guys will see lots of connections to your everyday lives in this unit. What I wanted to do is just quickly outline, this is a breakdown that I'll put into the Google Classroom under the lesson material for you guys in Unit D. And just basically talks about what I've just gone through. So we'll get a better idea about what electricity is, how it works, how to describe it, how to use it, how to make it, how to use it to make other forms of energy, those kinds of things. As always, there's pages in your textbook that you guys can use to go through. So concept D1, which is what we're covering today, will be pages 274 through 295. There is a whole series of videos that I put together for you. Some of them are more just interest's sake. Some of them will expand on what we've been talking about in this lesson as well, and I'll try to make reference to them in the lesson as we move forward. And then you guys will have some formative work at the end here, some stuff to get you ready before you get on to the summative quiz. So some questions out of the textbook. I will post a worksheet. I believe it's actually already up in the Google Classroom, and then in a short time I will also post a practice quiz that will be ready for you as well. So without further ado, let's have a look at the beginning of Unit D. I'm going to make that nice and big for you so you can see it. So Unit D is called Electrical Principles and Technology, and that is what we're headed through today. And we are going to get started on concept D1, which basically covers section 1 in your textbook. So at this point, if you haven't done so already, please make sure that you've taken out your notes, which you can find in the Google Classroom under Unit D, under Resources, Notes, and Worksheets. and grab them there. I don't know if you want to print them off or if you want to just have them open in a separate window and you kind of follow along that way. That's up to you. And then something to write with or something to take notes on in case there's anything you'd like to ask me later on at some point that doesn't quite make sense. Basically today we're going to run through some basics about electricity. So we'll talk about first static and then current electricity. We'll get into talking about electrical safety, and then we will talk about cells and batteries right at the end. And like I said, this is basically just a quick introduction to everything that's going on in this unit, and then we're going to do a deep dive into some of this stuff as we move through. So consider this kind of your introduction. There are a lot of vocabulary words, and don't worry about finding the vocabulary sheet. I'm not going to post that, but this was me just leaving this as a reminder to you that there's a lot of vocabulary in this unit. So make sure that you take the time to study that vocabulary. And I think I've said this to you before, about half of science, if not more, is understanding the vocabulary. So if that's all you have time to do, learn the vocabulary words, and I will be a happy camper. I left this in here as well, this little quick lab thing, because I think it's important. If you wanna try to play around, I would love to see. I'm going to post something on our Google Classroom for you to do through an app called Flipgrid, which allows you to record really short videos to me about what's going on in your world, but also I'm going to do this as a little bit of a fun assignment for you to do. So if you can do this, that would be great. The whole idea is to take a video of it and sort of show me that it can work. So if you can't find these materials, that's fine. This isn't necessary, but I thought it'd be kind of fun. Tie a 15 centimeter, about 15 centimeters of thread to a cork, and then rub a plastic straw, if you can find one, with wool or fur. If you can find a wool sweater around your house or something along those lines, or walk up to your pet and rub the plastic straw. And then what I want you to do is basically you've got the cork dangling from a thread and you've got the straw. I want you to bring that straw that you rubbed against the fur close to the cork and tell me what happens. Take a video of it and maybe explain what happened to me if I can't quite see it on the video. You might need help to do that. And then I have another follow-up one to do as well. Try this again by rubbing the plastic straw with the wool or fur, and then rub the cork with the wool or fur, and then hold it up. You've got your string and the cork dangling down from that, and bring them together and show me what happened in your Flipgrid video for me. I'm curious to see what happens, and then I'm curious to see if you can make the connections later on as we move through the rest of the unit. So pop off and do that right now, or go into the Google Classroom later, and I'll reiterate this in the little mini assignment I'm going to give you guys for that. Something fun for us to try. So first thing we're going to talk about is static electricity. And I'm going to give you a quick introduction to what static electricity is all about here, and I've got some videos that I'll give you, a heads up to whether you want to watch them or not. So before we get into talking about static electricity, we have to talk about what is the most important part, or one of the most important things for us to understand before we move into this big unit of electricity: the laws of electrical charges. Okay, and I think you guys know this already, but if you don't, just a reminder. If something is positively charged and something is negatively charged, opposite charges attract each other. And so that's what I'm showing up here, is that a positive and a negative will be brought together and attract. And then like charges, so if you have two positives being brought together or two negatives being brought together, they will tend to repel each other. Okay, so that's the law of electrical charges. That's important for us to understand as we move through the rest of the unit. And hint, this is a big idea for us. We need to understand what these laws of electrical charges are. So, speaking of electrical charges, objects are said to be neutral when the amounts of positive and negative charges are equal in them. And if you think back to Unit B, when you guys did ionic compounds, and you were constructing an ionic compound, you always had something that was positively charged and something that was negatively charged. And when we create an ionic compound, it is neutral. meaning the positives cancel out the negatives. Okay, that's what we're dealing with here, except we're talking about electricity. Okay, so an object may become positively or negatively charged when the number of electrons or protons in it changes. Now, I want to be clear here. We're not going to deal really with changing of protons, because when we change protons, we change the substance that we're describing. However, we can change electrons relatively easily. And I don't know if you've made the connection yet, but electrons sounds an awful lot like electricity. And so there's a big connection that I want you guys to make in there. So if we fiddle around with the number of electrons in particular, we can change the charge of something. When this happens, we say that if we can change the number of electrons in something, that the object has built up what's called a static charge. Okay, now let's move into static electricity. I think you guys know about static electricity already. You've probably encountered it at some point in your lives, whether you've reached up for something metal and touched it and got a shock from it, right? That is the release of static electricity. So static in static electricity is really the important part of this term, and I'll explain what it means in a second. But static electricity is the result of a stationary electric charge. Stationary, okay, means the charge is not moving. It is staying in one place. Static means the same thing. So static electricity is a stationary electric charge. It is not moving. So it's not moving because it does not flow in any way, shape, or form. Friction or rubbing objects together can produce static. So if you've ever taken a balloon and rubbed it against your hair and then stuck it on the wall, you've built up a static charge in that balloon from your hair, and it can stick up onto the wall. Okay, and that's what this comic is all about here, is that they've got nylon carpets. Well, nylon helps to build up charge on objects really easily, and so if they rub their feet along, that charge is being transferred to them, and that's why their hair's standing on end, the tie's standing on end, etc., etc. Okay, so how do we produce a charge? Well, charges, whether they're positive or negative, are produced when electrons move from one object to another. So there's electrons coming into play. Okay, so in order for us to create a charge, electrons need to move from one object to another. If the object has more electrons than protons, then we would call it negatively charged. And that makes sense. Okay, remember please that electrons are negatively charged, protons are positively charged. So electrons negative, protons positive. If you have more negatives than positives, your object is going to be negatively charged. If the object has more positives than negatives, more protons than electrons, it will be positively charged. And if the object has equal protons and neutrons, we consider it to be neutral. Those charges have canceled each other out. Remember, only the electrons move. The protons do not move. If they move, we all of a sudden create a different element at that point, and that's way more complicated than I want you guys ever to go into in this class. So it's the electrons that are doing the moving, okay, building up a charge. With building up a charge, charge separation can occur. And charge separation occurs when a charged object is brought close to a neutral object and separates the equal positive and negative charges, causing attraction. So here is a negatively charged, I don't know, let's call it a ruler, that has been brought near something called a pith ball, and don't worry about what it is. But what ends up happening is you notice that this is a neutral object here. But since the negative has been brought close to this, you can see that the positives have ended up being attracted to the negative in the ruler, and that the negatives have ended up being repelled by the negatives in the ruler. And so we end up having a separation of charges. Neutral objects will be attracted to charge objects because of charge separation. So what would end up happening if we did this is we would see that this little ball would move towards the negatively charged ruler because the positive charges are being attracted to the negative charges. Hope that makes sense for you as far as what's going to happen. So remember that quick lab I asked you to do back at the beginning. Maybe if you haven't done it yet, maybe go and build that into your response to me on Flipgrid as to what happened when you did that particular experiment. So once we've built up charge in something, we can discharge that object. So in order to discharge something, we have to build the charge up in the first place. So building the charge up, then we can discharge it. Static electricity generally does not move. It is stationary or static. However, if a built-up static charge on an object can be attracted, or a built-up static charge on an object can be attracted to other objects and jump to the other objects that it's attracted to. So often this creates a small spark, which is known as an electrical discharge. And I often tell this story mainly because it shows you how nerdy I was when I was a kid. But we would often go to my grandparents' house for Sunday night dinners, and one of my favorite activities at my grandparents', they had a really high quality carpet in their house, and I would be wearing socks and I'd be scooting around on the carpet with my feet, and then we would turn all the lights off, and I'd go up to usually there's a way to discharge on a light switch. If you touch the screws on it, especially if they're not painted screws, and I'd go up and I put my finger close to it with the light off, and you could see the little static discharge coming off of me to the light switch or whatever metal object it was that I was touching. That's how much of a nerd I was even back then. So this electrical discharge is basically the moving then of that charge from one object to another. It jumps over. So this is what happens when you walk across a carpet and feel a shock when you touch a doorknob or something else that is metal. You're transferring that charge. That charge is being discharged off of you. Hopefully you can picture that. One of the things pieces of technology that we can actually see this happening in is something called a Van de Graaff generator. And this is used to study electrical charges. Basically, it operates by having a rubber belt running in a generator that rubs against metal brushes, and it creates a static charge. And so that's what we have going on down here. And then the static charge is transferred to a metal sphere, which is over here, once the static charge builds up. So I've got a video that you guys can access in the Google Classroom under Unit D, under D1 Resources, Videos, etc. Have a look at this video. It's about 5 minutes long. It's Mythbusters, so it's entertaining. And it shows you that a little bit about Van de Graaff generators. So if you wanted to pause right now and go look at that, please do so. Okay, so we're going to move on then. This next bit here too, this slide is just to remind me to tell you I've got a couple other videos on there that you might find interesting about electric eels, who also can build up static charges and release them as well. So I'm going to leave it at that. At this point, if you wanted to pause, you could pause, flip open to 278 of your textbook and go through questions 1 through 5 just to give you an idea of what I think is important to pick up on this first subsection in section 1. So if you want to do that, hit pause now. If not, I'm going to continue on. So next thing we're moving on to is current electricity. So we've talked about static electricity, which is the buildup of stationary charge on an object, and that stationary charge stays there until it's given the opportunity to jump to another object through electrical discharge. Now we're going to move into the kind of electricity that we encounter most commonly throughout our everyday lives, and that is current electricity. And just to be clear, in this case, I want you to think of current as in the current of a stream. In other words, something is flowing, not as in current as in this is what's happening right now, if that makes sense to you. So that particular connotation. So current electricity. Static charges do not work well for operating electrical devices, right? They discharge very, very quickly, and then what are you going to do? you get a little bit of action out of that electrical device, and then that's it. So instead, we need something that provides a steady flow of electricity, right? If you think about your phone, there is a steady flow of electricity being provided from the battery in that electrical device, and it's providing a current. If we tried to operate our phones off of static electricity, we might, power up the screen, and then we'd have to go and charge up our static charge again, and then power it up again so we could type the first letter, and so on. It's just completely inefficient, not the way to do things. So we use current electricity. And electrical current is the continuous flow of charged particles. Okay, so static electricity was the buildup of charged particles. Electrical current is the flow of charged particles. In order for electrical current to exist, two things must happen. First, the flow of electrical currents requires an energy source. There needs to be something that is providing a flow of electrons. So that could be a battery. That could be a generator of some sort, like the generators we use to power our homes. Those are the big ones at the power plants that manage all of that kind of stuff. There goes my calculator. I just murdered it. It's on the ground. Anyway, carrying on. The second condition that needs to be met for electrical current to exist is the electrical current will not flow unless it has a complete circuit or path for charged particles to flow. So in other words, if there's not a complete circuit, and I think you guys have heard of circuits before, then nothing's going to happen. If you have a circuit but it's got a break in it, nothing is going to flow along because there's no connection to flow through that. Okay, so we need to have an energy source and we need to have a complete circuit for current electricity to work. What's related to current electricity is the idea of amperes. Okay, and an ampere is the rate at which current flows. Okay, it's a measurement of the rate of which current flows. And so the best way to think about it is to think about a fast flowing stream versus a slow flowing stream. Okay. Oh, and by the way, this is Andre Marie Ampere, which the unit amperes is named after. It can be thought of as the speed of the electric current and is often referred to as an amp for short. Okay. Electrical current refers to the number of electrons passing a point in a circuit per second. The more electrons, the more amps. The more electrons that pass that point per second, the more amps. The less electrons that pass that point per second, the less amps. So if you want to go in and learn a bit more about that, there's another video that I've linked to on the Google Classroom. Go and have a look at what is an amp. We are going to jump in a little bit more deeply into amps in concept B2 or D2, pardon me. So be aware that this is going to come up again. So speaking of circuits, one of the requirements that we talked about up here was that we need to have a circuit for the charged particles to flow. So a circuit, let's just be clear on this, is a path that controls the flow of electricity. Okay, we're going to dig into circuits a little bit more deeply, and we'll have some activities that you guys will get to do online to play around with circuits coming up in subsequent concepts. But a functioning electrical circuit must consist of three parts. It needs to have a conductor. A conductor is something that allows the electrons to move along that circuit. Usually our conductors are wires. Okay, the wires that we have in the circuits in our homes. The wires that we have in the circuits in our vehicles. They're basically wires that connect some sort of energy source, so batteries or the energy source that comes in from your house or a generator, to all the other parts of your circuit, and then ultimately back to that energy source again. So usually they're metal wires that make the conductor, but we can also conduct things through gases, fluids, and other substances, and we'll get to some of those later on in the unit. The other thing an electrical circuit must have is an energy source, and that energy source can come in the form of a battery, a generator, and possibly other things like a chemical reaction, which we'll talk about later on. And then lastly, they must have a load, and a load is the thing that we're hooking the circuit up for. So in this circuit here, this is our energy source. This line, ignore the switch, this line that goes all the way around here, ignore the fuse. Okay, that's our conductor, energy source, and our load is the thing that the electricity is working on. So it might be a light bulb. It might be a speaker that makes sound come out. It might be your computer screen. Okay, so you'll have a load. The thing that the electricity is making operate is your load. Okay. I wanted to talk a little bit about voltage. When we talk about current electricity, we always talk about amps, we talk about volts, and later on we'll talk about resistance, which we'll get to later on. Voltage is the measure of the amount of electrical energy carried by each particle. More voltage means more potential energy. So a higher voltage power source means that each particle has a whole lot of energy. A lower voltage power source means each particle has not as much energy. So voltage is also known as potential difference, and we measure voltage in what's known as the volt. Okay? For safety reasons, we keep most voltages quite low. In our houses, the average voltage coming out of a circuit in our house is 120 volts. But your stove, if you have an electric stove, operates off of 240 volts, which is very, very dangerous. 120 volts is dangerous, 240 volts is twice as dangerous. Okay. This video here at the bottom, again, is linked in the Google Classroom, and it would be worthwhile having a look at that. And it's talking about some of the safety associated with currents, amps, and voltage, and why we want to watch out for not only current but also for the voltage as well. To measure voltage, we use something called a voltmeter. Remember, a meter is something that does measuring. So a voltmeter is measuring voltage. Okay, when we set up a voltmeter, the red lead, and you may have one of these kicking around your house, particularly if one of your parents does any home repairs or anything like that, might be working on the electrical in cars or other vehicles. The little voltmeters look similar to what we have here, particularly these portable ones that we can carry around with us. The red lead must go to the positive battery terminal, and the black lead should go to the negative terminal to make it work. I have a battery back here, and if you guys aren't sure which is the positive and which is the negative, usually it's labeled on here. I don't know if you can see that, but there's the positive of this rechargeable battery. It's on a AA like this one. It's the spot with the raised bit, and then the negative end is that end on the battery. If there's more than one range and you're using a voltmeter, what you need to do is start with the lowest range first and see if it registers the voltage, and then continue to move it up. Don't start it on the top end, because you could end up causing some problems for your voltmeter. So we won't be face-to-face when we're doing this lesson, so it may be difficult for us to actually use a voltmeter, but I've got one. I can bring it out, and then we can play around with that a little bit. And yeah, we'll fiddle around from there. So at this point, if you wanted to hit pause, you can tackle these questions on page 283 of your textbook, and just give you again an idea of what I think is important from understanding current electricity. Now, moving on to electrical safety. If we're going to talk about electricity, and if you guys are going to, at any point work with electrical devices, it's important to understand some safety related to them. So, first things first, electricity has the ability to seriously injure or kill. Power lines carry electrons with thousands of volts running through them, and any person coming into contact with them may create an unintended path for electricity. So what that means is if you go out and touch a high voltage wire, you may create a circuit that runs between you and into the ground, at which point you've got thousands of volts worth of electricity running through you. That's why we tend to bury power lines or put them high up so we can't get at them. And when I'm talking about voltages in power lines, those high energy transmission lines are carrying tens of thousands of volts through them. Not just 120 volts like you would have coming out of your outlets in your house. 120 volts can be dangerous. 10,000 volts can be very, very dangerous and life-threatening. Electrical current can interrupt the function of nervous systems, your heart, both of which rely on electrical current to operate. There's actually little changes in charges that run up and down, or run down your nerves to certain spots that makes things happen. And if we disrupt that, you can stop your heart. You can mess up your nervous system in a big way, including your brain. High voltage is more likely to cause damage than low voltage. 50,000 volts are more likely to kill than 10 volts. And I'm sure some of you have gone and taken a 9-volt battery and stuck it to your tongue before. That's not going to kill you. It gives you a shock. It's not pleasant, but that's not going to kill you. Okay? However, we need to remember, high voltage is dangerous, but the number of amps is much more significant. So how many amps are running through that circuit is much more significant, because you may only have a few high energy electrons flowing through you if there's high voltage and low current. However, if there's high current, that means that there's lots of electrons flowing through your body at that point. More potential for disrupting what's going on in your body. So to give you an idea, if you had something that is at 0.001 of an amp, you're likely not going to feel the effect of that current running through your body. If you have something running at 0.015 of an amp, so that is about 10 times the amperage, you're going to get a painful shock. You might lose muscle control and not be able to let go of whatever object you're holding on to. To give you an idea of that, 0.1 of an amp is enough to burn, cause heart damage, or even fatality. Okay, so if this is something to give you an idea about, and it'd be worthwhile looking at some of your electrical devices and understanding sort of what the voltage is that's running through them. Have a look at them and see if you can figure out if there's something, you know, if you want to be electrocuted by that or not. Okay. In order to protect us from shock, we can use things called insulators. Things like wood or rubber or air to prevent the movement of electrical current, and it's going to help to protect you from electrical shock. So pay attention to the voltage and amperage labels on manufactured devices. The higher the numbers, the more damage the device can do if it malfunctions. And be aware of the location of power lines at all times. Locate the electrical breakers in your house or yard and know how to switch them off. I was doing some home renos over the Easter weekend here, needing to replace some receptacles upstairs in our bedroom, and I shut off the power to those rooms. I know my circuits on my electrical panel, and I was able to shut the power off to those and allow me to safely conduct that, because there is 120 volts of charge running through at a certain number of amps, and it could be enough that I could get seriously hurt from that. So I was being very cautious. There are some pointers on page 285 in your textbook. At this point, there should be some space in your notes to write down some of these pointers. I would invite you to take that time to write these pointers down. I'm probably going to ask you some questions about these in your formative and summative quizzes for this concept. So it'd be a good idea to go to page 285 and have a look at that stuff. I wanted to talk about plugs, fuses, and breakers, because this is an important safety device that helps us when it comes to electrical devices that we could be encountering in our lives. The third prong on electrical plugs connects to the ground wire of a building. What this does is it provides a route through which excess charge can escape to the ground, instead of building up and discharging through you. So if you have a 3-prong device, and I'm looking for one around me, but everything's plugged in behind my computer right now, so I can't really show it to you. That third prong, not the 2 flat ones at the top, but the third circular one, that is the one that is going to prevent a buildup of charge on you. And so if you go and you break those off, and some people do, you are removing a safety device from that particular cord or whatever it is you're using. So be cautious with doing that, because it could have serious effects if there's an issue with your electricity. Fuses and circuit breakers also limit the amount of current flowing through a circuit. If a fuse or breaker receives too much current, the circuit is broken and the current stops. And so I used to have, before we redid our kitchen in the house, we used to have a couple of circuits where if I was operating, let's say, the microwave and my popcorn maker, because I'm wanting to pop my popcorn and have my my butter melted as well, if I did that both at the same time, I would blow the breaker, because the microwave is pulling a lot of current and the popcorn maker is pulling a lot of current. And so instead of overloading those lines and creating a situation where we might fry the electrical devices or fry the actual cells, the actual wires themselves, the current, that circuit on my circuit breaker would break, would trip, and it would shut the power down to that current or that circuit before that current built up too much. The circuit breakers that we have in our houses are reusable, so we can trip them again and again and again without having issues. Some other kinds of fuses, like the ones that I have down here, you might find in your cars or other places, those ones will trip. There's actually a little piece of metal that will actually break in there, and you'll actually have to go in and replace them from time to time. So fuses must be replaced after they burn out, but a breaker can be reset after the problem has been resolved. I want to talk about lightning, just because it's kind of interesting to talk about, and it's a great example of electricity. The current in a lightning strike can be as high as 30,000 amps. Okay, so thinking about that, that is a lot of current moving through your body. That's enough to kill you, definitely, if not cause serious damage. So if you're, and we're getting into that season where we might start to get some thunderstorms, if you want to avoid being hit by lightning in a lightning storm, avoid being the tallest object or standing on or near tall objects such as rooftops and open windows, or rooftops and trees, and then stay away from open waters or any other conductors. Don't be standing next to a metal pole during the lightning storm, because you may just become part of that circuit as the lightning finds its pathway into the ground. Okay, so at this point, you can head on to the practice on page 287 and run through those questions. And I believe, yes, I believe the next lesson is on cells and batteries. And so I've already actually recorded that one last year. So you will have 2 videos that you guys need to watch for this particular concept. This video that you're watching now, and then there'll be a second video, I'll call it lesson 2, in your Google Classroom under Unit D. Have a look at that one after this, and it'll run you through cells and batteries. So that's about it for now. Don't forget, if you guys have questions, track me down online. We can get together and answer questions. Go back and have a look at the videos that I've linked in the Google Classroom. Don't forget to do the formative work, those practice questions on the pages that I listed for you. So there we go, the formative work here. And then there's also worksheet 1 on concept D1 that I'd like you guys to have a look at as well. Once you've done all of that and you feel comfortable, then you can move on to the practice quiz, which you'll find in the Google Classroom. Once I've gone through the practice quiz and provided you feedback, then you may go on to doing the summative quiz as well. Don't do it beforehand. If you have any questions, track me down online. Don't forget to move on to lesson 2 after you've done the formative work for this section, and do the next video in the Google Classroom. And as always, guys, stay healthy, and we'll talk soon.